We're really only going to have time. I'm not going to, we'll talk about this on Friday, exceptions. Exceptions are so easy. Once again, it's just fluff. You've done it the hard way. This is the easy way. And so it's really, once you'll see this, you'll be like, dang, that was pretty nice. And so it really is just fluff, okay? All this C++, a lot of this stuff is fluff. I do want to make you aware, C++, if you do not feel like you understood assignment 2 and assignment 3 very well, okay, if that's you out there, just take it as that is your 80% or 70% you didn't get in the class. It's life. You don't get everything out of a class. Period, point blank, okay? And, I mean, you can talk to any professor and they're going to tell you that. You're not expected to go to class and understand and remember 100% of the material fully. That's not going to ever happen for you. And so your goal is really just to, you know, even if you get one piece of information out of every class and that's one thing you learn, that's really good enough. You know, I was told when I took photography where you develop a roll of 24, was it? You know, even as professional photographers, if they can get one picture out of that roll that comes out fantastic, they feel they're doing a good job. And when I heard that from a professional photographer, it put a real good perspective on what you in life should go after, okay? You're never expected, even as a professional, to get it right all the time. It's stupid. It's human nature, okay? So take that as that. We're done with C++ for the most part. I could still go over a couple more fluff things. This assignment is a really easy assignment. This assignment I used to give to my students, non-CS students, as their 1D array assignment in week 6 or 7 or whatever of CS1. So that's all the material in here. File I/O can either be in a CS1 or a CS2 class. We just decided to move it into this class, but it's not rocket science, I promise you. Okay? You've done a lot more complex stuff than this assignment. So take a breather. Maybe also work some on your other classes, because I am going to tell you the next assignment will be a doozy again. I know you'll all struggle with it, because I even had good students who struggled with it last year, okay? We're going to be in C, you're not going to be in C++, and it's pointer hell. Okay? And so linked list in C is pointer hell, and we've got to enter that world again to get ready for 261. I advise most people, in the fall, you really want to take 261. I don't know what advice you're getting, but that is my advice coming from a computer scientist. From the beginning of CS, we always took CS1, CS2, data structures. You take it in that sequence. And in many schools, you don't even go into any other classes until you take that sequence. So just make sure, guys, that if you can fit it in your schedule, I'd rather see you in the fall so it's fresher on your mind than in the winter for 261, okay? What I've heard from students, I know this is going to be a hard assignment, but I've heard that it will carry you through about 4 weeks of 261 pretty good, okay? I like that because I think that gives you a little head start, and it gives you a little break to get comfortable with some other classes if maybe you've got database or some other CS classes you'll be taking at the same time now, okay? So let's visit this for just 1 minute, because this, I want to make sure everybody does understand this, because it is due on Wednesday, and I won't have office hours. I don't have them on Monday and Tuesday, and so I just want to make sure you need to at least start thinking about this. I don't think it's going to be a hard coding project, but be thinking about it, okay? If the main thing you're thinking about is the math, that's not where I wanted to stump you, okay? That wasn't the point of this. I want you to learn something new, but I'm not trying to stump you with the math, okay? So what I want you to realize is what we're dealing with is some kind of function of space and time, okay? Our space is one-dimensional, and so what we're always looking at is at some particular space on the X, and at some particular time, U is going to give us back this temperature, okay? So the outcome from U of xt, when you plug in some X and plug in some T, should be a temperature value, Okay, that's the idea. This is what you're looking at, okay? So when you say u of 0, 0, that's looking at your, this is your x, right? What we know is it goes from 0 to n, okay? When you're looking at 1, 0, you're looking here. Who said, ah? It'll start making, I know I heard that somewhere in the audience, because everybody always goes, oh my, this is way easier than I thought it was. So you have this, okay, you have this medium here, and we're only looking at one dimension, and if you do the two-dimensional, I'm going to put that on there, but that'll be your extra credit, okay, if you want to do two-dimensional. Okay, so here you go. You have these as your initial on both ends. You also start them out with all zeros in here, right? 0, blah, 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 all the way to 0. There's a bunch of zeros in there. You do not mess with this one. This one never changes. This one never changes. You are interested in 1 through n minus 1. Right? That's the x values you're interested in finding temperatures for. Okay? So you're interested in finding temperatures at each of the x areas, right, or x spaces, and at t plus delta t, your new time instant, okay? This is still 0, this is still 100, okay? Notice I have 2 arrays up here. If you see 2 arrays on your piece of paper when you're trying to mimic this in real life, you're going to have 2 arrays in your program. It's as easy as that, right? That's why I try to get you to put things down on here. If you want to use a two-dimensional, you could do that, I guess. But I would use this. One thing I did tell the earlier, okay, what you were doing, guys, is you were using what's called the explicit method. That is what you're doing right now. There is something out there called the implicit method. You're not doing this one, okay? So it may seem weird. I understand that it seems really weird that I'm calculating this only using the stuff up above. So in other words, when I'm calculating my new temperature here, I am using these 3 values. When I am calculating my temperature here, I'm using these 3 values for this one. When I'm calculating here, I'm using these 3 values. Okay? That's the explicit method. Implicit method in the real world would be that, of course, once I found what happened here, and especially on this side, if I found this thing changed right here based on this, why wouldn't I use my new changed stuff? Right? Why am I still using something from up above when I know in time it has changed? That's the implicit method. That's what we would do in the real world. It's the approximation, of course, is much better and much more accurate with an implicit method than an explicit method. Okay? Your approximation, you also get more, you get better accuracy if, of course, this n is equal to 100 versus equal to 10. Okay, this be now 1 centimeter apart versus maybe 10 centimeters apart. It just all depends on what your initial length is, okay? But that fine grain, so what I've started talking about now with you guys is something called Big O, okay? This is your time complexity. Okay, I'm going to start talking more about this because this is all the crux of your 261 and something that's been lacking. So you'll go more in depth with it when you get into the different algorithms, and the different complexities get different with different algorithms. But you need to be starting to think right now in terms of loops. Okay, loops add complexity. Constant statements are just constant. We say Big O, constant time, just constant. It's not based on anything. Okay. We start talking about time complexity when we start talking about loops. This, of course, has to be a loop to go through each of these places. You can imagine if you have, and you're talking about the Earth where you're doing this, okay, for climate modeling, and you want to see, you want fine grain, you need to see something in every, like, 100 square mile, right? That would be a nice fine grain. Now we're doing it over 2 dimensions, and you can imagine the more accuracy we get, the more time it's going to take to do this, okay? No matter what, this is an approximation, okay? The reason I like for you guys to know this is because there's not the integration and derivative. These are such great problems because we don't have this in the computer. It doesn't exist in our computer, okay? We have to approximate. We have to write these functions. If you wanted exact, people would have to sit down at, you know, NOAA and calculate this equation for each one of their little places by hand, right? Because they would be using this. They would be doing it by hand, doing this. Oops. This one up here, taking derivatives, and then finding and plugging in their x's and doing all of this, okay? They're not going to do that, okay? So instead, we're going to sit there and we approximate things, okay? But then when you approximate things, I can't write on that. When you approximate things and they're not exact, so calculus doesn't mean a whole lot to us as computer scientists, to be honest. Calculus doesn't mean a whole lot in the real world because, trust me, we're not doing this with calculus, we're doing this with approximation. Your climate, your weather comes back to you every day as approximation, okay? Your bridges get built and stuff by approximation. Everything's modeled by approximations because we do not have a way to put calculus in the computer. Doesn't happen. We have to come up with these methods that will give us approximations. And it just so happens that when you do a partial derivative, and that just means that this is a function of space and time, if I want to do a partial derivative with respect to either time, or I'm going to do a partial derivative with respect to space x. And it's partial because it's to one of the things in there, okay? It just so happens that this is the way you do heat diffusion, okay? That is the equation for anybody that does heat diffusion. How they came up with that, that's the science in it, right? I just get this stuff from the scientists that say, hey, this is what I need for you to compute, okay? And then you have to say, oh, okay, well, what do I know about all the methods I've learned in computer science for when we need a derivative or when they give us a formula with an integration or an integral? Then we have to plug in the things that mean sense to us, the algebraic way of doing things, okay? Discrete math. We kind of need to work in that realm. So, anyway, when we look at this, you can see that what we're trying to calculate is that we're trying to get this temperature, right, at some x value, 1 through n minus 1. So we're trying to get the new temperatures, some new temperature, new time, 1 second later, hour later, however often they want to calculate this weather or heat diffusion, right? And all that has a lot to do with, think about that, that's your loop. The quicker they make those, the more they want to do those, the longer it's going to take to calculate, okay? So your loops, when you have something, a loop, and you have that for however many elements in my array, right? And we take that fine grain down to, we want to make 100 elements, not 10 elements, because we know the approximation is going to get better, right? What did we do? We now took that loop and we made it that n is now from 10 to 100, because a loop by itself, its big O is n. Okay? What you're looping, how many times you're looping through. Okay? That's your time complexity. When you do this for a two-dimensional space on Earth, you do not double your complexity by having nested loops. You actually exponentialize that time complexity. So now you go from n to n squared, okay? Just by nesting a loop inside of a loop, all right? 1,000,000 squared is pretty hefty time complexity, okay? Hence, why we have supercomputers, because now if I can take and put 1,000 of these n's on each little processor, now I've beefed myself back down to an n that's 1,000 maybe rather than 1,000,000, right? So time is actually, what you've been working on you see your results come back fast, okay? But this is actually a pretty big deal when we get into real-world problems, okay? And so now I have to start talking about, because complexity is a pretty important aspect, and you're going to start getting into triple loops and like that. You get into a triple loop, you got n cubed, okay? It just keeps getting worse and worse and worse. Anyway, so that's just a quick, there's something out there called Big O. Start looking at that. And we're solving for this. That means multiply delta t over here, multiply delta t over here. Divide by this CP or rho over here, divide over here. Plus this term over here, plus it over here, right? Now what do you have? Everything on this side to get your new temperature, right, from 1 to n minus 1 is all based on what? Where was that one? Previous, exactly. So you're using, so this is what makes it the explicit method, right? Because you are using this right here, this one, to calculate this one, all right? Does that make a little bit more sense to you guys? Very easy. I promise you. It is super, super easy. Do you have any more questions on this? To make sure that you understand the mathematical aspect. Go look at it. You'll be fine. Ask me if you have any questions. But you shouldn't, don't worry. The part really that you should be struggling with on this would be the mathematical aspect than anything, okay? But it gives me a good time to talk about time complexity. It gives me a good time to talk about what do we have to do as computer scientists to, in the real world, for other people. And it doesn't always match up, guys. Okay? All right. Now we're going to go back to templates, okay? So let me show you. Let's do a template demo, okay? So we're going to write our own vector class. We did this in the class before, so I should have enough time. So we're going to write our own vector class. And I'm always learning something with you guys. That's why I love to teach new classes and learn new languages, because I get to learn. I love being a student. And so as I was writing this vector class, I thought, this is pretty crazy. And we're going to get there. So I went up to a professor to find out, and I'm glad that I finally know, so we're going to have a little bit more insight on why we have .hpp files, okay? And it's not just people being willy-nilly and needing to they want to just mix their implementation and their interface. When it comes to these templates, it's almost how you want to do it, because otherwise it's just stupid the way it's done. And it just is what it is, okay? And apparently the syntax for it, and it just was kind of generics and stuff in the C++ is a little weird and kind of been an added-on feature and something they've been tinkering with every single standard and version, that it's just a weird thing, okay? And so I'll share it with you, what I learned, because I think that's the best way for you to learn too. And so let's go for it. So if we were to start off, I'm going to tell you about, I'm a student with you, right? I do stuff just like you do, like you would at home, okay? So I teach you make vector.h. So I made a vector.h. What's in our vector.h? How do we make a templated class? What was that little thing I told you we had to have at the top? Template. Whoops. If you want to be an insert mode. Template. And we have to have this weird, okay, we're going to have some type in there that we don't know what it is, right? Some templated type in this class. Oh, what am I doing? Class. What's our class name? Vector. Can we make things a vector? All right. What do you think we have private in here in a vector class? What kind of an array? So what does that look like in the beginning? Like a pointer, right? Thank you. Good job. What else do we have in here that's private? Size. Good job. Naming it S, because when I did this at home and I named it size thinking I was doing a really good thing, and then I had a function called size and needed to return size and size. It didn't quite want to work out with me. And so I guess I could have put this in front of it, so I could have made a distinction between my scopes. Anyway, we're going to name it S. What are we going to have public? Okay, but first we should always think about our constructor. And why is that, Gadir? Okay, we're just gonna do the destructor for now. You can go and do the other ones, okay? This is an exercise more on how you want to work with templated classes. Okay, what do we have? We have a pushback. What is it going to return? It doesn't really need to return anything, right? We're going to push back. What's it going to get? T. Good job. T. That's exactly right. We're getting a T. All right. Look good? Well, we could go with all of that. We are just not going to the whole vector class in 15 minutes. But for right now, we're just doing this little tiny bit, okay? Also, this is a good way for you to realize when I'm at home and doing something, I'm trying to get you to realize I'm a student with you, okay? I just don't go wildly trying to do more than I can handle. I make myself say, do I feel convinced at this stage? Do I feel convinced at the next little stage? Do I feel convinced at the next little stage? I don't go implement the whole dang vector class. That would be absolutely absurd, okay? So I want you to get in that mentality. It'll help you be better programmers, I promise you. So for us, for right now, remember all we're doing is implementing pushback. Would this be good enough for right now? And I would expect for you to do the other big three, okay? But for right now, say I was being good and I did those other ones. Okay. Now you would all go, I need a vector.cpp because that's what Jen told me, right? What do we need to include? Okay. What are we going to implement in here? Well, we're going to implement our vector. What does vector need to do? Create, well, do we need to create the array? When we're giving it nothing, what does it need to do in the beginning? If you haven't set capacity, you haven't done anything, what happens in this default constructor? Null, good job. So our V is going to be set to null. And S is going to equal 0. Good job. Now that we have null in here, pound include what? C standard lib, or else it's not going to know about that little dude. Okay, and I wouldn't put the template thing up there because I was thinking, oh, well, that's not really a templated function. It doesn't have T in there. I'm just going to leave it without it, right? Okay, this was all my thoughts, okay? So I'm just going through with all this. Now, vector, scope it, our destructor. And what does our destructor have in it? Just delete our B. We don't need to check for null because remember we learned that. That was something I was being over crazy about because that thing itself checks for null and doesn't do anything. So it's just redundant to check for null. You don't need to do it. Okay? You can if you want to. It's just overkill. Okay. Now what else do we have? Now we have one of these that has T in it. So I said, oh, okay, well, I'll remember that I need this. Because it's got to see something about this T. Okay? Oh, whoops. What were we giving it? And it returned what? Remember, T is just whatever type we make it. Could be an object type, could be some class type, could be a character, could be an int. We tell it when we make this thing. That's the beauty of this templated class. Okay? We don't have to make it one for characters, one for integers, one for la la la, right? Okay. All right, so in here, how are we going to handle this? What, excuse me now?
It's pretty much like making the array and
It is, so tell me how we do this. What's the thought process? What would you think about?
would you put the original array in the temp?
Exactly, Heidi, we would have to do that because otherwise you're not going to be able to do this. That's exactly right. You have got to have a temp array. Why did you say that? What made you think to do that? What temp? What the hell am I doing? Sorry, guys. I wanted to call it temp and I start making a temp. Obviously, you're not talking type at the same time. What were you saying, Heidi?
We have to copy the values into another one.
That's right, because I can't just go and delete it and make a new vector, or else I've lost all the values in that vector, right? Okay, so I need to make new of what type? T. How many? Size. Do I need one more? Not really, because this is just to hold the old thing, right? Or at least this was my thought. You could do it on your own. Implementation could change. Now what do we need to do? For loop, good job. I less than S, I plus plus. What's going to be in our for loop? Good job. Perfect. Okay. Now, what can I do now? Yes, I can. Well, first I need to do. First I need to. No, first I need to delete the sucker. Right? Because I've got to reallocate this. What else happens? So I needed to delete B. I need to, my size has changed because I'm pushing 1. Pushback is only pushing 1, right? Yeah, good job. Now we get the S plus 1. Then what happens? Now I need to make V.
Size S.
Yes, good job.
And then copy temp UV.
Good job.
And then you have to put probably in the last element.
Okay, so do I need to go to S here, or where do I need to go?
Sorry, S. Oh, that's swap the S.
Yeah, well, I know that. So we know this, that I'm putting temp back into V. And where do I need to go? I incremented my S. Thank you. S minus 1. Good job. Because we incremented our S. After this, what do I need to do? Be at S or S minus 1? S minus, good job. Good job. That's exactly right. Now what else do we need to do? Because me being a moron forgot this the first time I did it. Good job. Delete the temp. Because what would we have if we did not do that? Bad memory leak every single time you call pushback. That would not be good, would it? There's no other way to get something off of there. Okay? All right. Do we like this? I like it. Okay. Now, we need to make some kind of thing to try this out. I called it TriVect. What have we known about this? What do we do? What do we include?
Vector class.
Vector class. So we pound include.
Vector class.
How do I make a vector? Vector. Let's just make it events. We'll change it to chars if we have time, right? V, can I have a V here? Yeah, this is a different scope, different code, different V. Okay. How do I call that pushback? Let's put some kind of number in there. Okay. So first of all, I want to convince myself that I don't get any segmentation faults and everything like that. This is how I work at home, okay, when I work by myself. I would do the most bare minimum to make sure I get no seg faults, but then after I know I have no seg faults, everything appears to be working correctly. Would that right there be enough that would convince you, that enough testing to convince you that pushback was working? No. What would you do to make sure that you understood it was working without overcomplicating this? Well, I mean, I guess you could do something like that too. I would make, because if we're writing this, at this point, I would make a size and I'd make an at. Has a size and an at. That way I can look at the at, go see, is the 23 in there, right? And then I can make sure my size is 1 after doing this one pushback. And that's what I would expect, okay? But when I do this at home, I do very, very small stages for everything. Maybe because I think I'm a moron. Trust me. All right. There's somebody that's going to make a mistake. It's definitely me. So I have, you know, found love in making mistakes, I suppose. All right. What do we do now? Right now, let's just convince ourselves that we have set everything up correctly and everything, okay? And that pushback is at least not going to give us a bunch of seg faults and everything else, okay? Or anything. Okay, what now? We got to build it. Okay? The first time I went like this in the class right before, and a student said, oh, you forgot to bring in the .cpp file, the vector.cpp file with this. I said, well, that's a pretty good assumption based on what the compiler just said right here, right? That'll be your first thing? That's what we've learned. Oh, and now we have all this other kooky stuff. Where would you go in this situation? What would y'all do? You know what I would do is I'd pull out a book. This is why I like books, okay? Because your book is probably the first place to go look at an example. Am I doing this like an example out of my book has it? Okay, that's why we ask you to buy books. Okay? When I go and look at your book, the one thing I notice in your book is that they have this thing going on here. They have that, okay? And for some weird reason, they have to put this above every single one of these functions. Even when it seems like, why the heck am I putting it there? The T's not in there. Okay? This is really interesting. Yeah.
Is it because E is pointing to T's?
It's just because we have it in a separate CPP file. I'm about to show you. Okay? Remember, I told you my whole entire thing was to come back and tell you why you see these HPP files. This is about to be one of them. Because, of course, to me, in my syntactical little mind, especially when I teach compilers and everything else, I'm like, this is stupid. Why am I having to do this? So I went into a faculty's office, and I'm learning C++ with you guys. And so I went in there, and I said, you know, I said, what on earth is this? I said, that's about the stupidest thing I've ever seen. You're making me put this above every single one. It doesn't look like it's doing much for me. And then all of a sudden he said, you remember when I talked to you about there's this time when you want to do your implementation and interface at the same time? I said, oh, I said, that's the .hpps. And he was like, yes, you don't have to have all of those if they're in there together. And I was like, that's why they do it, because this would be crazy to remember. My feeble mind would not remember this at all, okay? So let's go back. We're going to do a couple different things here, okay? So I look at your book and I see this, and I'm like, oh, okay, great. That's going to fix my problem, right? It's not going to fix my problem. So I go back and I get this again. And the whole thing that fixed this problem was me bringing in the compiling it with the vector.cpp. So I'm back to the same problem that we originally thought we fixed the problem with putting the .cpp with this. What would you do again? Me, I go back to my book. I look at this, I look at the examples just a little bit harder to say, what am I missing in here? Because I read things fast. I miss things. You know, you're human. You read fast. Okay. So when I go back in there, I see, wow, They are not including the .h. So now it just defies every dang thing I taught you. They're including the .cpp file. What? That's what I said too. What? So I was like, crap, I've just told them everything wrong. I don't know what's going on here. Well, I didn't tell you everything wrong. Templates are the one and only time you mix these. And mainly because of that funkiness that you got to put this T in this template class above every single function, and you're going to have to remember that, and I just think it's pretty hard to remember all that, okay? So, now we go G++. We included this, which is interesting. And oh my goodness, it worked for me. And I was like, yes, but I don't like this. Ugh, right, this was all set. When I talked to a faculty member, I said, oh, remember the HPP and this, well, first of all, he said, if you put them in with the class, you don't have to do all of that. And I said, oh, so much nicer. He said, hence, remember when we had, I said, oh, now the HPP discussion makes much more sense that we had. Didn't make a lot of sense at the time when we were discussing it, because I had not been here in a situation where I needed it, right? And it's really hard if you haven't been in a situation to know when to have a conversation with somebody and know where they're going with something, right? That's why I like being a student, because I know how you feel at times, okay? I'm totally with you. I'm in your court. So I said, okay, so in the last class we did this, and it worked out great. How do we move? So what we did is, because I have a couple minutes, and I know I can do this. How do I move, or how do I change the name of a file? Move. No, I was not doing a very good job there, was I? Move. And I'm going to move this into a vector.hpp file. Okay? Now let's go back and do my vector.hpp. Okay? And am I still going to need this .h? Nah. Because I'm putting everything together. Okay? In the last class, I forgot to take that out, and of course it'll give you a redefined, and all you got to do is get rid of it. We still need one template class T. Class vector is what we're naming this, right? You told me that we have a private. Let's make a T splat V and an int S. Public. Whoops. And I'm just not going to do a bunch of spacing stuff here. And we're going to get rid of this because we don't need our scope operator if we're inside the class. So that gets rid of that whole scope operator. Lovely, because that was weird. We can get rid of all of these. Get rid of that. Whoops. We don't undo. If you ever do that, just you undo. Okay? And then what do we need? We need the last thing to finish off our class. These will all be public. Same exact thing we just implemented, right? This looks a heck of a lot cleaner to me. And I don't have to remember everything, okay? What do I need to do? And try vector. That's right. That is a lot cleaner. So this is the one time when I will say, guys, you should mix your interface and implementation. And this is the one time where C++ does this too, okay? Since this is a video and it's hotter than crud in here, let's get out of here. And if you want to make your own size and act to convince you that this all works, then you do so, okay?